I'll try to not write on the board for that reason because that doesn't get recorded. Okay, so if you're an organized person, great. Block out, like I took some time management class, as a freshman in college. They made us during orientation go to something. It really works if you print out a schedule with hour blocks and you literally say, these are the 2 hours I'm doing chemistry between chemistry on Monday and chemistry on Wednesday. And you just block out 2 hours. So that is the approximate amount of time you should be blocking out between each class session. Sometimes it might be only 1, sometimes it might be 3, maybe even 4 before a test. Okay? First key to success. We will set up your Pearson after class. Hopefully everyone has submitted that pre-class assignment. If for some reason you are having tech issues or just added, you can do the assignment over the weekend and just email me, and then I'll take off the late points. Okay? Forget this thing about discussion because I took that off a year ago, so I'm not sure why that's still on there. And then files. You should be good. Okay, any questions? Technology, orientation, course structure. We'll get you stuff you need after. Okay, so we're jumping into chapter 10 today, and I am going to do some review on chapter 9 for those of you that didn't have it from me just a month ago or 6 weeks ago, or for those that, I don't know, completely lost their brains from the last 6 weeks. So we'll do a review of chapter 9, not the whole thing, but the stuff we need going on. Primarily electron configurations and orbital diagrams. So you don't necessarily need to have this robust view of quantum numbers, but how that then translates into where the electrons are, what orbitals they're in, that's what's going to be important. Okay? All right. Very first thing should be review, but let's see. Why is this not shrinking down the way I want? I'm not happy with this app. I feel like they've changed things. Okay, go ahead and quickly try to categorize each of these compounds. You can't even see the whole thing at once. Usually I'm going to close it and open it back up and see if that helps. So I want you to categorize them as ionic or covalent. Okay? Google it if you have to. How do I know if something is ionic or covalent? If you're new to me, usually I'll say I'll give you 2 minutes, and then halfway through, I'll start to work the problem up here. So if you're not lost, just go ahead and keep working. If you are, you can always look up and get a hint. So there's your first hint if you need it. Okay, if you had to Google it, first thing that should have come up is an ionic compound is a metal and a nonmetal. Okay, covalent compounds are all nonmetals. How do you tell the difference? Let's go ahead and pull up a periodic table really quick. Oh, why don't I have the exam equation sheet on here? Grr. Let me just add it because we'll want it up there. That's probably why. There we go. Updated. Oh, that's not the right place. Oh well, it'll work. Okay. Periodic table. Little fancy line here. Things that are on the line have similar properties to both, have some properties to metals, some to nonmetals. These guys are your nonmetals. These are your metals. Okay? Most things are metals. All right. So that should be pretty straightforward now, that all you have to do is look at where it's at on the periodic table and decide if it's a metal or a nonmetal. If it has both, then it's ionic. If it only has one, then it's covalent. Okay. Often we talk about these as electron transfer, which we will explain in more detail in a second. We'll say that about ionic. And in covalent, we talk about them as electron sharing. Now, what that usually does, because they are significantly different types of bonds, is it has a big effect on their structure, like how they physically look. So when we talk about electron transfer, just really simple example, we're talking about the fact that when sodium and chlorine interact, the sodium loses an electron to become sodium plus. The chlorine gains that electron to become chlorine minus, and then they're held together by that very simple, what we call electrostatic force. So gravity is a force. I'm going to drop this pen, not the $100 Apple pen. So gravity is a force of attraction between the pen and the center of the earth, and they always want to be closer, right? Any two things that are attracted to each other want to be as close as possible. Same thing with positive and negative charges. They're attracted to each other. There's a force of attraction there, and they want to be as close to each other as possible. So that is the essence of an ionic bond. You get two charged particles, opposite charges, and then they suction together. That's an ionic bond. It's pretty darn strong. It does not have individual units the way a molecule does. So if you have a bunch of sodiums and chlorines, instead of a sodium and chlorine going off by themselves and a sodium and chlorine going off by themselves, a bunch of sodium and chlorines come together and form one big mass that looks like this. So you'll notice like this sodium is completely surrounded by negative chlorines, and any given chlorine is surrounded by positive sodiums. So it like maximizes those positive negative attractions for every single ion that's in this crystal. This is why we usually see ionic compounds as crystalline, because they are a big mass of ions, and if you want to break them apart, they just naturally break on these kind of lines in the structure. Lines like where there's a split between the positive and negative atoms. Okay, so when we write the formula for an ionic compound, we are not writing how many there are really of each individual ion. We are writing, and we're also not even showing what the charge is on the ion. We are just writing down the ratio. So sodium chloride has a 1-to-1 ratio of sodium plus ions and chlorine ions. Because covalent bonds are electron sharing, they behave a little bit differently. So they are not just one big mass of positive and negative ions. They are individual interactions between the atoms, and that results in what we call molecules. Now, there is water up there. I don't love that picture as much. So we're going to look at pentane down here. So 5 carbons and 12 hydrogens. This is not just a ratio of carbon to hydrogen in some big mass crystalline structure. It is individual units that have 5 carbons and 12 hydrogens. So if I had something that had 10 carbons and 24 hydrogens, which could vary, it is a real molecule, that would not have the same properties as C5H12 because they are not one big mass of things. And just because they have the same ratio does not mean they're going to have the same properties. In fact, pentane is probably a very thin liquid at room temperature, whereas decane, it's probably decene, that is going to be probably a very viscous liquid at room temperature. Okay, so they are not going to have the same properties even though they have the same ratio. And that's because they form these little individual entities that we call molecules. The other thing that's kind of important differentiation between ionic and covalent is what bonds or forces are broken when we either melt or boil them. So if we were to, at the bottom here, it says Google their melting points. I am your Google for this morning. If we were to Google their melting points, you would see that ionic compounds have high melting points. We're talking like 1200 degrees Celsius. Very, very difficult to melt salt. You can easily dissolve it in water, but that's a completely different process. We're talking like straight salt, you stick it in a pot, like you're gonna have a pretty hard time melting that, okay? A covalent compound, on the other hand, is super easy to melt. The fact that pentane is a liquid at room temperature tells us that at room temperature, there was plenty energy to melt it. It's already melted and turned into a liquid. Or think of like a simple fat, like butter or coconut oil or something like that. It's a solid at room temperature, but it doesn't take a whole lot of energy to melt that, right? In fact, I think coconut oil is like body temperature is enough. So you like stick it in your hand and you can melt it. So we'll say medium melting points. The reason why this is the case is because you actually have to break these ionic bonds in order to melt sodium. So melting requires breaking ionic bonds when you're talking about an ionic compound. Now, covalent bonds are not weak. That's often what people think of when they think, oh, well, they have relatively low melting points. They're like, oh, covalent bonds must be so much weaker than ionic. No, that's not the case. When we melt ice, we are not breaking covalent bonds. So water in the gaseous form, it's still water. It still has those covalent bonds holding the hydrogen and oxygen together. It's simply because they form these little units, they have a different way of melting or boiling. So again, the pentane one has prettier representations. These little dots represent what we call intermolecular forces, and we'll do these in chapter 12, I want to say, maybe 13. So relatively soon, we'll talk about the forces that hold together covalently bound molecules. So they form these little entities, and that's where the covalent bonds are. The covalent bonds are in here, holding the carbon and hydrogen together. But when we melt those compounds, we're breaking apart these interactions between the molecules, not the bonds within the molecule. And that's why we see them having significantly lower melting and boiling points. Okay, so those are some ways we can differentiate ionic and covalent, and then some properties associated with them that cause them to have, well, some characteristics that cause them to have different properties. And then for the rest of class, we're going to talk in more detail about their bonding. And bonding always goes back to valence electrons. So we're going to have to hit back on where those valence electrons are, what a valence electron is, how we know if they're high or low in energy, where they are, what given orbital they're in. We are not going to talk in any detail whatsoever about metallic bonding. That's what would hold together all metals. So think of like, you have aluminum foil. It's probably mostly aluminum. that's held together. All those individual aluminum atoms are held together with metallic bonds, and it's a very different property. It is why it allows metals to like conduct electricity and heat really well, but we just don't go into a whole lot of detail in here. I won't test you on anything. You can read about it if you want. Okay, any clarifications on identifying those, telling them apart, why they have the properties they do? Okay. We are, because you read this in the textbook, I know already, we are going to look at a way to represent the valence electrons for every given element. Where do I want to write down this thing about valence electrons? I'm just going to open a blank page. I'm going to do it on here. Last class, I did it on this is always fun when I open up my random boards. You can see how bored my children are in church. This was supposed to be a niffler. Do you see it?
I see it.
We had just gotten back from Harry Potter World, and one of my kids bought 2 different nifflers, and so he was drawing a niffler. It's either that or like sleeping on mommy. Okay. We need to review orbitals in order to talk about Lewis dot structures. So I'm going to do this for a simple ionic compound, sodium chloride, and then maybe, well, don't let me get the charges off of there first. And then maybe we can move on to something a little bit more complicated like sodium and sulfur. Okay, so starting with sodium and chlorine. I'm going to start with orbital diagrams because I think that is the easiest way to visualize what's happening. Once you can picture an orbital diagram in your mind and connect that with an electron configuration, then you probably don't have to keep drawing the orbital diagrams. And I probably won't always draw the orbital diagrams. But since we're all wanting to make sure we're in the same space and we all are on the same page, we'll start with drawing them today at least. So sodium is 11 electrons. It's in the 3rd principal energy level, the 3rd row. And chlorine, same principal energy level, 17 electrons. Okay, so I'm going to draw my typical orbital diagram. And I always draw them vertically so that things that are closer to the bottom are close to the nucleus. So to represent the nucleus, I'm going to put plus 11 because that's how many protons are in the nucleus of sodium. And for chlorine, we'll go ahead and start that one, plus 17. And I'm going to draw out the orbitals. If you are like, oh shit, I have no idea what she's talking about, you need to go back and review chapter 9. Okay? You can always read, you can watch the videos, you can do some of the practice problems at the end of the chapter. This is what I mean. You don't have to know like L equals 0, M sub L equals whatever. We don't have to know it to that extent, but you do need to know that the number that I'm writing here, 1s, 2s, 2p, that represents N, which is the principal energy level, which tells us how far away from the nucleus these places where the electrons can be are. So 1s is like this, 2s is like this. It gets bigger, okay? The s's are spheres, and the p's are little dumbbell shaped, okay? They have 2 lobes, we call them. That's probably the extent you need to understand the quantum mechanics-ness of it. We also want to remember that the closer to the nucleus equals lower in energy. So just like I talked about with gravity, if the pen is up here, it's high in potential energy. This is like 8th grade physical science. This is high potential energy. It is attracted to the earth or to the table or whatever. It's not the table, it's the earth it's attracted to. So if I drop it, it's going to go to low potential energy all the way to the floor apparently. And that's because it's attracted to it. Same thing with the electrons. If they can get closer to the nucleus, they will. okay? They want to be at the lowest possible potential energy. The electrons all fill in the same general way. They have the same labels for all of their orbitals. The only difference is that the orbital energy changes slightly based on the atom that we're talking about. So at the very end of Chem 1, we talked about the fact that chlorine is smaller than sodium. Because it has more protons, the electrons get sucked in tighter. Okay, it's like literally thinking of the nucleus of chlorine is stronger because it has a greater positive charge. So when I draw them, I will usually try to draw them slightly closer. Even though it's a 2s and a 2p, the 2s and 2p are slightly closer in chlorine than they are in sodium. Okay, and then we keep going. 3s. Good, we don't have to mess with D's, although I did that in my other class. 3s and 3p. And then with higher energy levels, we would go on to like the 4s, the 3d, the 4p, etc. Just as kind of a side note, because I mentioned this in my other class and I like to stay consistent about what I said, when we talk about valence electrons, which are the outermost electrons, so I'm going to block those, highlight those out in yellow. So for sodium and chlorine, these are going to be our valence electrons. If we were dealing with something that was one row down, so say boron instead of, bromine instead of chlorine, we would have filled d orbitals, the 3d subshell. When we put a letter and a number together like this, we call it a subshell. So the 3d subshell would be filled with bromine, but we do not consider that to be valence electrons. Even though when we write out the electron configuration, we would include it. So like an electron configuration for bromine would be 4s2, 3d10, 4p6, 5. We would write it out, but we don't usually think of the d electrons as valence electrons because they don't participate in bonding. So it's usually just the s and the p that we're worried about. This one doesn't matter because we don't have any d electrons here. Okay. So sodium, 11 electrons. I'm going to go ahead and just fill them in. 1, 2, we always fill in lowest energy first because that's where electrons want to be. If they're able to be at that low energy, that's where they're going to go. Every orbital, which is represented by the line here, can hold 2 electrons. And if we have, so I'm going to put 2 more in the S's. If we have 3 orbitals, in the case of a p subshell, we get 3 of those dumbbell-shaped orbitals. That subshell can hold a total of 6, because each one can hold 2, but they fill in individually first, and then they start to pair up. So this happens anytime that they are equivalent in energy. You can see this in my diagram because I've drawn them all at the, I've drawn them horizontal, like so that they're at the same horizontal energy level. Okay, so the next ones I go fill in, I'm at 4, 5, 6, 7, 8, 9, 10, and then my 11th one is going to be up in that 3s orbital. Okay, so the only valence electrons that sodium has is 1 electron in the 3s. Okay, I'm going to translate this back to electron configurations because that's a very tedious way of representing the electrons in sodium. It's super helpful, but I'm not going to want to do that every single time. So I can write that down as 1s2, meaning there's 2 electrons in the 1s, 2s2, 2p6, 3s1. So I'm saying as the superscript is telling me how many electrons are in that given subshell or energy level. There's also even a shorter way to represent that, the abbreviated electron configuration. which I go to the noble gas that is one row lower in energy, the N equals 2 in this instance. And instead of writing 1s2, 2s2, 2p6, which is the electron configuration for neon, I just write neon in brackets. And then I finish off with 3s1. So this is particularly helpful for bonding, because what it does is it isolates the valence electron there. So anything past that noble gas, you can pretty much say those are the valence electrons, and those are the ones we're going to care about when we talk about bonding. The other ones, those are called your core electrons, and they're so close to the nucleus, they're so tightly bound, tightly attracted, that they don't end up bonding with anything. Okay, chlorine, 17 electrons. I'm going to start the exact same way. I'm going to fill them all in, lowest energy orbitals first. When I get to the 3p, I'm now at 8, 9, 10, 11, 12. So I'm going to fill them in one at a time in each orbital and then go back up and pair them. What did I say? 10, 12, 13, 14, 15, 16, 17. So I end up with 3s2, 3p5 as my valence electrons. And the abbreviated way to write that is still neon, 3s2, 3p5. Or I could write it the long way, 1s2, 2s2, 2p6, 3s2, 3p5. Okay? But the short way is nice because it tells me my valence electrons. Okay, here's the nice thing about ionic bonding. It's so straightforward. I have one electron here that's high in energy, and I have one open spot over here that's low in energy, lower. Why is it lower in energy? Because chlorine's smaller, so that orbital is closer to the nucleus, which makes it lower in energy. So all that's going to happen is this electron is going to transfer over to that chlorine. So I'll keep it in black to show you that it's different than those green electrons. It came from the chlorine. And I'll erase it from the side. So now sodium is no longer sodium, it's sodium plus. I'm not going to talk too much about the electron configuration, but we just got rid of that one. Okay. Chlorine now gains an electron, so it is now chlorine minus because it has 18 electrons and 17 protons. Sodium has 11 protons and now only 10 electrons. Okay, and now they stick together, sodium plus and chlorine minus. That is an ionic bond. That is how it happens. And that's why we call it electron transfer, because it's moving from one atom to the other. Okay, let's move back to the notes really quick and just look at the first three elements. So lithium, beryllium, and boron. And then I want us to do the next row. So this is just a slightly different way. Instead of doing an orbital diagram, which is probably more complicated than we need, we're just going to draw the valence electrons surrounding the symbol. So for the next row, sodium, magnesium, and actually let's do the whole row. So we're going to do sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. So I want you to do that underneath here. I will try to write small as well. So I want you to do the same thing for the elements that are immediately below on the periodic table, each of these. And just, not AG, AR, and just represent the valence electrons. So if you want to first because I do ask, write the abbreviated electron configuration. If you want to write the electron configuration first, if you want to just think about how many valence electrons it has, but draw them as dots, and similar to how we do orbital diagrams, we start by drawing one dot around each side, so 4 different sides, and then we double them up. It doesn't actually matter. Like, I usually start at the top and go around. I swear Lewis was like a little neurotic, and he was like, you gotta start on this side and you gotta blah, 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 whatever. So hopefully, pretty quickly, you see that they have the exact same number as the one that's above them on the periodic table. So since the beginning of Chem 1, we've told you, I'm going to switch over to the periodic table here. Yeah. We've told you that in the first column, there is 1 valence electron. In the second column, there's 2 valence electrons. We skip over the transition metals because they are weird. The third column, 3A, is what it's labeled as, 4 valence electrons, 5 valence electrons, 6 valence electrons. We're just giving a visual representation now for this fact. Did I skip over something? I skipped over 5, didn't I? 6, 7, 8. Okay? This is also how we know that group 1 is going to lose 1 electron when it participates in ionic bonding. Okay, as I write these charges, this is only ionic bonding, not covalent. Second group, it's going to lose both of those valence electrons, plus 2. Third group is going to lose all 3 of those valence electrons, plus 3. We just saw with the sodium chloride example that chlorine has 1 open spot. That's why it gains 1 electron. So let's go to sulfur to prove that sulfur has 2 open spots and gains 2 electrons. Nitrogen and phosphorus have 3 open spots, so they will gain 3 electrons and become -3. These columns are invaluable. Okay, there is no way to place value on how useful the structure of the periodic table is. Oh, that's not where I wanted to go. Let's go back to our pretty picture of orbital diagrams of sodium chloride. And you know what? Instead of redrawing the whole thing, I'm just going to alter it slightly. Okay, so I'm going to leave sodium how it was. And we know that it forms sodium plus, but let's just go back to sodium real quick. So it was like this. And now let's look at sulfur instead of chlorine. Okay, sulfur is going to have 1 less electron than chlorine did. Just making sure I'm using the same everything. Okay, so this is sulfur. So pretty quickly, you should see that it has 2 open spots, right? You can kind of even see that on those Lewis dot diagrams, right? If there can be 2 around every of the 4 sides, you really quickly know how many open spots there are, right? Sulfur has 2 open spots. Chlorine only has 1 open spot. Both with ionic and covalent bonding, when something is already paired up, that means it's not going to form a bond, okay? It is already filled up that orbital. There's not going to be a bond forming. If there is 1 electron in an orbital, that is a very good indicator that a bond needs to form there somehow. So in an ionic bond, the way that happens is it grabs it from a metal. So still in this case, sodium's going to contribute an electron to that sulfur, but the catch is that now we need another sodium atom. So we're going to give ourselves another sodium atom, and we are just going to pull that electron over as well and fill in that sulfur with 2 electrons. Now, hopefully, it makes clear sense why, when sodium and sulfur form an ionic compound, you have to have 2 sodiums for every 1 sulfur. So I'm going to get sodium plus, and sulfur 2-. Okay? Now, when we did stuff in first semester, we just said, oh, they have to even out to be 0. So you need to have 2 sodiums for every 1 sulfur because sulfur is in the 6th column, and so it has a -2 charge, and that's true. But now hopefully you see orbital-wise why that's the case. Sulfur has 2 open spots in that valence shell, and it fills them in by taking 1 from one sodium and 1 from another. Okay, how does this end up working with covalent bonding? So, covalent bonding, we already talked about similarities. They have the same number of valence electrons. Select a metal and a nonmetal. We just did that with sodium and sulfur. And 2 sodiums will bond with 1 sulfur and form sodium sulfide. Okay, this is why there's always a set ratio for ionic compounds. You're never going to have like Na3S or NaS2. It's always a set ratio because they're always having to give up and take the same number to fill in those empty orbitals. Okay, now instead of sodium and sulfur, we're going to look at oxygen and sulfur. So this would be a covalent bond that we would be forming because these are 2 nonmetals. Okay. Oh, that's not even the one we're going to do, are we? When we draw the actual bond. We're going to look at sulfur and hydrogen. But we want to compare sulfur and oxygen first. Okay. Oxygen looked like this. So it's in 6th column, 6 valence electrons. 1, 2, 3, 4, 5, 6. So pretty quickly, we should think oxygen could form 2 bonds. Either it could gain 2 electrons from a metal, but let's focus in on covalent bonding now. It's also going to have the tendency to form 2 covalent bonds. Not absolutely every time, but very often. Sulfur looks almost identical. Okay, so they both have 6 valence. I always do this. I always get ahead of myself. I make this is not like I copy the notes from the textbook. I make my own notes and then I just forget what I was going to say. Okay, so actual electrons, oxygen has 8 and sulfur has 16. Valence electrons, oxygen and sulfur both have 6. When we talk about octet, we're talking about filling the S and P orbitals, which is where that 8 number comes from. So we've got 6 around there already. We have 2 open spots to fill in those S and P. We call this the octet rule. It's more of a guideline than a rule, but it's pretty good. So we have 2 open spots to fill in to get that 8. The 8 comes from filling the S and the P. So each one of them would need 2 additional electrons or form 2 covalent bonds to make it stable. So very similar to ionic in the sense that you're trying to fill in that valence shell, those S and P orbitals. It just does it in a slightly different way. Instead of an electron moving from one to the other, we are going to find one that can also fill its orbitals at the same time as it's helping the other atom to fill its orbitals. Let's ignore this for now. So let's go on to the hydrogen sulfur thing because that's more cohesive. All right, hydrogen, what does hydrogen look like? It's got 1 electron. We need to draw its orbital diagram really quick though. It's very easy. It looks like this. Okay, hydrogen is slightly different. It does not have an octet to fill because it doesn't have any p orbitals. So we don't have to worry about that. We call this a duet rule. It's kind of ridiculous. Just know that hydrogen only has to have 2 electrons total because it only has that 1 s orbital. Everything else has to have 8 because it has 3 in the p and 1 in the s. So it's filling in a total of 4 orbitals for 8 electrons. Okay, so how many bonds is it going to want to have? 1. Hydrogen will only, this one's firm rule, hydrogen will only ever form 1 bond. Sulfur, oxygen, from what we drew before, looks like it wants 2. Hydrogen's only ever going to form 1. So sulfur, let's do this based on the dot structure that we did before. Sulfur looks like this. Hydrogen looks like this. And then we'll go back to the orbital diagram at the very end and show you what it looks like in the orbitals. But since we're going to use these Lewis dot for the rest of the time, it's a good way to do it. Okay, so instead of the hydrogen giving its electron to the sulfur, it is going to share it. So let me do the thing again where I draw the electrons in a different color so we can see where they're coming from. So this guy, I don't like that. I'm going to move it. Let's like make them come close. Okay, here they are. Ready? They're coming closer. They're coming closer. All right. Now, what happens is that these 2 electrons, hydrogen gets to claim them for itself and fill its 1s orbital. But sulfur also gets to claim both of them and fill in one of its empty gaps and its p orbital. And this is what we mean by sharing. They both get to count both of those electrons. So it doesn't move, but rather they claim them both as their own. And that's what we mean by sharing. Well, we still have a gap for the sulfur. So we can be pretty sure that if hydrogen's around, what's going to happen is it's going to come along with its electron just like the other one did, fill in that gap for sulfur, and also, thankfully for it, it gets to claim sulfur's electron for itself. So sulfur shares 2 electrons, 1 with each hydrogen, and the hydrogen gets to grab one of sulfur's electrons and share it and fill its 1s orbital as well. So the way we would end up drawing this is with a line. Anytime there's a line, that represents 2 electrons being shared between the 2 atoms that it's connecting. And we call that a covalent bond. Those electrons on the sulfur that are pairs but not bonded up to anything, we call them lone pairs or non-bonding pairs. Lone, not because they're still a pair, but they're on a single atom, not bonded to another atom. All right, last thing, just for fun. We're going to change our drawing again, and we're going to show hydrogens, individual electrons, what the orbitals looked like. Okay, so same thing before with the sulfur. It had those two empty spots. But now, instead of the electron actually moving, we're just going to bring these hydrogens close, if I can. There we go. And we're going to let them live in both orbitals. Both electrons are going to live in both orbitals and be shared between the two. And what this literally means is that those electrons are attracted to both nuclei. So when we draw a bond, I'm going to draw them as dots right now. When we draw a bond, what we're saying is these electrons are attracted to this nucleus and this nucleus. That's really what we mean by sharing them, is that they now get to be attracted to two nuclei, which is why it's so beneficial, because it's like you have something you're attracted to, but now you have two things to be attracted to. So it actually lowers their potential energy even more to be allowed to be attracted to two different nuclei. Yep.
So hydrogens, dot gets to be attracted to both nucleuses, but none of sulfurs gets to be attracted?
The one from sulfur, so this one gets to be attracted to this hydrogen, and this one gets to be attracted to this hydrogen, but those guys stay with sulfur. Yeah. So when we draw these representations, because like pretty much from now on, I might do it one more time, but pretty much from now on, we will just do these Lewis representations. So yeah, you need to get that these electrons are just attracted to the sulfur, whereas the ones that are going to be represented as a line are an electron from sulfur and an electron from hydrogen that now get to be attracted to both nuclei. And that's what lowers its potential energy and what makes it a bond in the first place. So to break that bond, you have to actually like break the attraction to both nuclei. Okay. Was there a hand back there?
I was just double checking it lowers the potential energy, but you said it again. So.
Okay, good. All right. That was fun. The second class is always better. The first